Allora, tutti quanti devono accettare, quelli che sono collegati. Tutti quanti devono accettare, quelli che sono collegati. Allora, buonasera a tutti. Io credo che mi conoscano in tanti. Sono Giorgio Patrizio, sono il presidente dell'INdAM. Con grande piacere do il benvenuto a tutti i partecipanti presenti in sala e a quelli lontani collegati in vario modo. Do tutti il benvenuto a questa quarta edizione del Colloquium INdAM. Diciamo che questa iniziativa è nata per iniziativa appunto del Consiglio Scientifico dell'INdAM in un momento, diciamo, sicuramente non felicissimo per tutti quanti noi. Probabilmente non avremmo pensato a questo tipo di iniziativa senza la stagione del Covid. Ora sembra che la vita stia tornando alla normalità e anche la nostra professione stia tornando alla normalità. Però, diciamo, questo tipo di stare insieme almeno una volta l'anno sembra sia stato molto gradito e ha un senso di diciamo, confermarci come comunità allargata di colleghi e di matematici italiani. Diciamo che trovo questo tipo di occasione, almeno una volta l'anno, un'occasione importante. L'INdAM è l'Istituto Nazionale di tutti i matematici italiani e quale miglior modo per celebrare questa forma di universalità, questo collegamento che abbiamo, se non diciamo, offrendo un'opportunità di stare insieme partecipando a una conferenza. Anche oggi abbiamo una speaker prestigiosa. Ringrazio moltissimo Lucia Caporaso per aver accettato l'invito a fare questa conferenza e invito tutti a essere partecipi. C'è la possibilità di fare domande anche sulla pagina YouTube, verranno raccolte alla fine. E niente, buon pomeriggio a tutti e sono sicuro sarà un pomeriggio di grande matematica e una bellissima occasione per stare insieme godendoci la conferenza. Grazie e cedo la parola al professor Bracci che presenterà la nostra speaker Lucia Caporaso. Grazie a tutti.
Grazie Giorgio. Allora, presentare Lucia penso che vorrebbe più di 2 ore per tutte le cose che ha fatto, quindi io mi sono fatto una breve sintesi, così poi Lucia potrà invece parlare di cose ben più sostanziose, non che la vita di Lucia appunto non lo sia. Allora, Lucia nasce a Roma nel 1965 e si laurea alla Sapienza con lode nel 1989. Poi consegue il dottorato di ricerca, il PhD, presso l'Università di Harvard con John Harris nel 1993. Resta ad Harvard poi nel 1997 e contemporaneamente è stata ricercatrice a Tor Vergata dal 1994 al 1997. Poi dal 1997 al 2001 all'MIT di Boston e dopo una breve parentesi di 2 anni all'Università del Sannio diventa professore ordinario a Roma 3, dove è tuttora. È stata plenary speaker all'Unione Matematica Italiana, invited speaker all'European Congress of Mathematician e International Congress of Mathematician. È stata Eisenbach Professor all'MSRI nel 2019 e nel 1997 aveva già vinto il premio Bartolozzi. È socio corrispondente dell'Accademia delle Scienze di Torino. Inoltre non ha fatto soltanto matematica, ma si è distinta avendo fatto moltissimi ruoli istituzionali, anche pesanti. In particolare è stata coordinatrice del dottorato, direttrice di dipartimento, membro del Senato accademico e del CDA di Roma 3. Io ho avuto modo spesso appunto di confrontarmi con Lucia per varie cose ed è una delle persone diciamo più intelligenti che si possano trovare in ambito istituzionale perché ha buon senso, praticità e tutto quanto. Quindi, da un punto di vista scientifico, membro del comitato editoriale di varie riviste, tra cui Transaction of American Mathematics Society, Memoir of the American Mathematics Society. E è stata principal investigator di svariati progetti di ricerca e attualmente anche del PRIN, l'ultimo che è stato finanziato ancora. Dobbiamo vedere quelli nuovi. Il suo campo di ricerca è la geometria algebrica, la geometria aritmetica, quella tropicale e la geometria enumerativa. Inoltre, Lucia ad oggi, ho controllato prima su Mazzenet, risulta aver pubblicato 43 articoli, più credo un libro, giusto? Ed ha ben 851 citazioni. Ha pubblicato sulle riviste più prestigiose al mondo, tra cui Invenciones, Duke, Journal of American Mathematics Society, Journal of European Mathematics Society, CREL, Transaction of MS, Advances in Mathematics, Journal Algebraic Geometry e così via. Il suo lavoro più citato sono 102 citazioni su Invenciones del 98, in cui ha studiato e generalizzato le varietà di Severi delle curve piane e ottenendo una interessantissima formula ricorsiva per il loro grado, come conseguenza di equazioni di cicli. Poi ha fatto così tanti lavori e poi, non essendo io in realtà un esperto di geometria algebrica, quindi mi termino qua e quindi ringrazio ancora Lucia per aver dato la sua disponibilità a questo colloquium dell'INdAM e quindi lascio la parola. Il titolo del suo seminario di oggi è Moduli Space and Rational Points of Algebraic Curves. Grazie Lucia.
Grazie, thank you Filippo. You're making it hard for me to speak now. I thought I would give my lecture in English, but you have been speaking in Italian. So
as you like.
I thought, there may be people who don't speak Italian that are listening, so I will give it in English if that's okay.
Okay, that's fine.
All right. So thank you for the nice words you said about me. But especially I'd like to thank INdAM for this invitation. I'm very, very happy to be able to accept it. Thanks to Giorgio Patrizio, thank you to Filippo and to Professor Canuto also, I hear he's online. So the theme of this colloquium is the interaction between geometric and arithmetic properties for algebraic varieties. So we have arithmetic on one side, geometry on the other side, and we try to understand how one aspect influences the other. So this is the general thrust. So this is a colloquium, so I want to make it as accessible as possible. So let me start to tell you how algebraic geometers think. Algebraic geometers algebraic geometry is the perfect setting to study the interactions between arithmetic and geometry, as I mentioned. And it's not clear yet, but it will be in a moment. So let me tell you how algebraic geometers think. And the main thing is algebraic varieties can be thought of in two different ways. They can be thought of as abstract objects, or they can be thought of as concrete objects embedded in some ambient space. To even begin to talk, one needs to fix a field. So in this talk, F would be a field. And not any field. The only fields we will be interested in are right here. This has the field of rational numbers. So all of our fields will contain the field of rational numbers. So this would be the smallest of all. Then let me leave some space to mention some well-known fields. The algebraic closure of the field of rational numbers, the field of complex numbers, and here we will put number fields. number fields. A number field, you can think of it as just a finite extension of Q, or even better, something that you get by adding to Q just one element. So you can think of K as something of the form Q of A, where A is some element in C, which is algebraic over Q. So it's just a finite extension of Q. Once you have our F, so F would be general for these four types of fields. Once we have this F, we can talk about ambient space. So let's start by looking at concrete algebraic varieties. So what is the ambient space? The typical ambient space is the projective space over F. What that is, I remind you, is just a set of n+1 tuples of elements in F. You take out 0, and you take the quotient by the relation that tells you that two tuples are equivalent if they're obtained one from the other by multiplying each coordinate by a non-zero scale. So this is a projective space, and the reason why we like this very much is that if you look at it, so this is the projective space where F is the base field. But you can also, let me erase this. You can also look at it inside Pn of C. F is a subfield of C, so there's a very obvious way you can do this. But now when you look at this projective space over C, you can think of it as a complex variety. And as a complex variety in the classical topology, this is compact. And so are all its closed subsets. But what's more important is this is precisely why you want to look at projective space, because its complexification is a compact object. And that makes life very easy. So also all closed subvarieties in here will be compact once you look at them over C, which is why we look at projective space as ambient space. The reason why I'm apologizing about this, which it may sound that, why are you justifying this? Well, the reason why I'm apologizing is that when you look at, now I want to tell you what projective varieties are. Projective varieties are given by zero loci of polynomials in projective space. The problem is that to talk, since a point in projective space has homogeneous coordinates, so it doesn't have only one set of coordinates, but it has infinitely many, because you can multiply all coordinates by some scalar. You cannot speak about the zeros of a polynomial in projective space. It's not correct. But you can speak about the zeros of a homogeneous polynomial, which is why when you look at algebraic varieties in projective space, you have to look at homogeneous polynomials, which is something, a little less elementary. But anyway, so what is an algebraic variety over here? We take a subvariety over here. We take some polynomials. We take a set of polynomials. Let me write it this way. Let's use alpha, F alpha. F alpha is a homogeneous polynomial in n+1 variables. Homogeneous. We take this set of homogeneous polynomial for alpha in some set of indices A. Then you can, let's give this set a name, T. So this is a set of polynomials. Finite, if it doesn't matter, you can always reduce it to a finite set. Then an algebraic variety in F, which we call zeros of T, and I will abbreviate this as Z of T, is just a set of points in projective space F over F, Pn over F, such that F alpha of P is 0 for every alpha. This is the typical algebraic variety. Projective, which we say is defined over the field F. All right, this is just a definition. So the point to keep in mind, if you have never seen such a thing, is that we are only interested in functions that are polynomials. We are not interested in exponential functions. We are not interested in transcendental functions of any type. We're not even interested in square roots functions. The only functions that matter for us are polynomials. So our varieties are defined by the vanishing of polynomials. I wrote homogeneous, I didn't write polynomial, but I meant homogeneous polynomial. All right, this is very general. Let's look at an example. So I want to start with an example that will be here. I hope this is okay. So let's consider the projective plane. And let's look at Q as our field. Okay, so we look at P2 over Q. And I take one polynomial, a very explicit polynomial in 3 variables. I have to take a homogeneous polynomial in 3 variables. So how about this? X to the d plus y to the d minus z to the d. The zeros of this polynomial is then a subvariety, an algebraic variety in the plane. And let's give it a name. Let's call it CD. D at least 1. So what are the points on this? We are over Q here. So how does this variety look like? I use the letter C here because this is what we call a curve, as in the title of the talk. Most of the talk will be devoted to look at curves. So this is a plane curve of degree D with a certain equation, very simple equation. So what is it? If b is equal to 1, we have a line. So it has infinitely many points. So this is just a line. If t is equal to 2, you think about it for some time, you see that this equation, there are lots of x, y, and z where this has rational solutions. In fact, there are lots of x, y, and z integers where this has solutions, because the x, y, and z here are the Pythagorean triples, where x and y are the sides, and this is the, I don't know how to say, what do you say in English? Hypotenusa, whatever. So it's an infinitely many. It's an infinite set. What about d at least 3? This is these were easy. This is an extremely hard question. In fact, maybe you recognize what question this is. This is the answer to this question is there are exactly 2 points, and these are the points of the obvious one, 1, 0, 1, and 0, 1, 1 in homogeneous coordinates. But that this is the actual answer took a long time to prove. This is Weyl's theorem in 1995 of the famous Fermat's last theorem. This is the Fermat curve. So this is just to convince you that it is very difficult, very, very difficult, even when the equations are simple as that one, to describe this loci. This is over Q. Now, let's look at the same thing over C. So this is, in fact, inside, as I said before. C. So what about the points? So this is over Q here. This is not a good notation. Now you may complain. So what do you mean by CD? Do you mean CD over Q over C? What do you mean? In fact, this is a very bad notation. I'm going to have to change this. But so what do we do? Well, since you see this polynomial is a polynomial with coefficients not just in Q, in any field containing Q, you can view the zero locus of this polynomial not just in PQ, but in any field containing Q. And so how do we tell what notation do we use? Well, we use the following notation. For any f, as I said, f contains Q. We write CD of f. This is the same as saying the points of CD viewed over f. So viewed as a subspace of projective space over f and with coordinates in f. So this is what we call the set of f rational points of CD. Equivalently, if you look at CD inside projective space, those are the points which will admit a representation with coordinates all in F. Okay? So here, this is not what I wanted to write here. What I want to write here is CD of Q. Okay? So let me do it on the board. What I described for you here is CD of Q. And now this is unambiguous. Now, as I said, I want to look at the set of points over the complex space. This is an entirely different situation. If we take the complex space, this is always uncountable. It's infinite and it's uncountable. Okay, of course, I'm taking D at least one. Okay, so it's a completely different story. Now, so of course, we will use this notation not only for our curve CD, but for all sub-varieties of, so we'll see what I mean. But what the point I want to make now is, this is, I don't want to only say this. I want to say that this is, this object here has a geometric invariant that plays a role for us. So far we've been talking about arithmetic. We've been talking about rational points. That's what we call arithmetic, or Diophantine properties. So when I listed my fields here as Q, K, Q bar, and C, what I had in mind is that here we're doing arithmetic. Here we are more classically doing geometry. And what we want to know is what's the relation between the two. Okay, so when I talk about arithmetic, I'm here. When I talk about geometry, I'm here. And the issue is, how do we go from one to the other? Okay. So now let me speak about the geometry of this. This is a curve over the complex numbers. So even though over the complex numbers this has dimension 1, you can look at it as an object of R over the reals. Over the reals, it has dimension 2. C has dimension 2 over the reals. Hence, anything that has dimension 1 over C has dimension 2 over the reals. And as such, CD corresponds to a real surface. Compact, I told you before, this is why we're looking at projective spaces, because they are compact and connected. So it looks as follows. If the degree is 1 or 2, then this is a sphere. If the degree is higher, this is a Riemann surface, an orientable surface with G holes, and G depends on D. G is D minus 1 choose 2. So this is the geometry of that curve, the main invariant of that curve. So this picture is telling us that in the first two cases, if the genus is 0 and 0, you have infinitely many cases, infinitely many rational points over Q. If the genus is 1 or more, you have a finitely many, but you have some. This is not very nice. Doesn't suggest much. And it gets even more complicated. It gets even more complicated if you look at other curves. Let me give you another curve, another type of curve, just by changing that definition a little bit. Let's put a plus sign here. Okay, and so let us call this, let C prime D x squared plus y squared, D plus yd plus z. Again, this is a curve of genus D minus 1 choose 2. The genus formula only depends on the degree you have here, as long as the polynomial that you are defining the curve with is of degree D and irreducible. Okay, let me not get into this. This is technical. Okay, so this is another type of, it's a different curve, but the equation is very similar. So what about its rational points? If D is 1, again, you have a line. Everything is fine. Nothing changes. Lines are easy. What if D is 2? You think about it for 1 minute and you see that if d is equal to 2, that you have no rational points. This is empty. And the same holds for 4, 6. I leave it to you for all even degree. If the degree is odd and greater or equal than 3, I will leave it up to you. Let's not do that. Okay, it's not easy. But again, you see there's a huge difference again between this case and this case. Here in degree 2, you have no points. Here you have infinitely many. Again, also in this case, the same picture we have here works. Okay, so from the complex point of view, CD and C prime D are very similar. We need to work out some details, but that's how it is. So the point of this introduction, it's not really an introduction, the point of this first part is to convince you that to find rational points of, even for plane curves, is very hard. It is hard. It's not just the degree that counts into the picture, there's more, okay? Which is why we now begin to speak about abstract curves, not just curves in projective space. So what is an abstract curve? Well, you can think of it, so abstract means somewhere in outer space. Okay. So you can think of a curve as something that's locally adaptive as a finite union of open subsets, each of which is isomorphic to some open subset of a projective curve in the projective space. Okay, then you have to glue these finite open sets, and then you have charts. But this is essentially how you think of it. To any abstract curve, always projective, and in fact, to any algebraic variety, to any projective algebraic variety, you can associate hundreds of models in projective space, and to every projective variety, you can associate its abstract model. All right, so you have this interplay, but this plays an issue for us, as you will see. So from now on, when I say curve, I mean C is a curve, by which I mean smooth, which means that locally, the tangent space at each point is just a copy of C. So you don't have crossing, you don't have weird things, curve, smooth. Projective, connected, and I will not repeat that, of genus G. So if it's defined over Q, when I say of genus G, I mean that its associated complex curve is an algebraic structure on a topological surface of genus G as the ones I drew before. So an orientable compact surface of genus G. Defined over some, let's say Q. Over some field Q. I want to start with the rational numbers. Okay. What about its rational points? This is a new theorem, also another pillar of Diophantine arithmetic geometry in the second half of the previous century, which tells us the following. So this is a theorem. Then we have two cases. If the genus is 0 or 1, then there exists a number field. It's not true. We cannot say anything about the rational points of Q. As we said, we have cases where that set is empty, cases where that set is finite, cases where that set is infinite. So we cannot possibly hope in a clear-cut statement. But as clear-cut as we can get is this: there exists a number field K such that the set of rational points of Q over K, which I told you can be defined, because if C is defined over Q, then it's also defined over K. I haven't told you what rational points are yet, but I will. Okay, but that's it. That you can wait for a moment. is infinite. This is not so difficult. What's really difficult is this. If the genus is at least 2, then for any number field k, the set of rational points is finite. You might recognize this is a very famous theorem. This has been proved by Faltings in '83. Faltings, sorry for this terrible handwriting, Faltings, and this is the proof of the Mordell conjecture. The Mordell conjecture. So here is where we see that geometry, as many people will say, influences arithmetic quite strongly. There's a huge difference between these two cases. And now, in 2 minutes, let me tell you how. I still have to tell you what rational points are. I haven't told you. So I told you the rational points for a curve in projective space are the points with coordinates in that field, in the field you're looking at. But these curves are abstract. So how do we define rational points? Well, we could, but it's really ugly. We could take any model of the curve in some projective space and then use that definition. But then you might wonder if that depends on the model. So in any way you flip it around, you're always bound to have to do what I'm going to tell you now. You only end up having the following as a good definition, which is something which is very nice because it's very elementary, although it looks terribly sophisticated. I'm in it. So the first thing is to think about is what is a point in geometry? What is a point? A point is a point. I mean, Euclid already knew that, right? In algebraic geometry, a point by itself is not just a point, because in algebraic geometry, a variety is specified not only by its topological space, but also by the functions by the polynomial functions you can define on that space. Otherwise, it wouldn't be an algebraic variety. You wouldn't be talking about algebraic variety. You would be talking about a topological space. Okay. So a point in algebraic geometry has to have some functions. And to say that the point is defined over some field, I told you with O, is a point such that the only functions that you can have on that point are the constants in F. So the functions are given by F. So this is what a point over F is. A point plus the fact that you have built in the definition that the only functions you can have on that point are the constant in functions with values in F. And this has a notation which is horribly ugly, but that's the notation we have. And this is this, spec of F. So this is a point in algebraic geometry. This means a point over F. Okay, now what is a point over F in an algebraic variety? Let me go again to with the analogy with topology. I mean, algebraic geometers have this terrible habit of confusing points with maps and maps with points, and it's a continuous. Also arithmetic geometers do that all the time, right? Points become maps and maps become points. But this is not. It's not just a way of being complicated and of scaring people, because of course, if you are in topology. I say topology because I mentioned it before. You can still think of a point in a topological space as a map from a point, the topological point given by one point, which is unique. You can take that point, you can take a continuous function from that point to your space. And that is, if you take all functions from that point to your space, you have a way of parameterizing all points in your space. It's just that it's not interesting in topology, because you might as well speaking about the points of the space. But in algebraic geometry, it's very different, because if you think of all the maps from your point spec F to your, so I'm taking all the maps, but since I want, this is home. I'm in a category, so I'm looking at the maps, and I'm maps in the category of algebraic varieties. That's usually what home stands here for. if I look at all maps from spec F to my variety V, where V is any variety defined over F, I have a way of telling you which points of V are defined over F. And these are exactly the rational points of V. So this is the new definition of rational points, F rational points. Which supersedes the one we had before. The point is that for any morphism from our point over F to V, you see that in any embedding of V in a projective space, that point will have F coordinates, coordinates of F, and converse. To any point in any projective model of V with F coordinates, you immediately, it's very easy, construct a map from spec F to that point. So this is an intrinsic definition of rational points that does not depend on the embedding. So this is now the statement of the Falting's theorem, and also the first part of the statement uses that definition. Okay, so I wanted to put that on the board because it will appear a little later if I manage to finish what I want to say. Okay, so now that I told you what rational points are, if there is any question, maybe I can stop. Maybe I have to wait until the end of questions. Yes, let's do that. Now I want to tell you just a little bit about what goes into the proof of this theorem. I will, of course, very little. So I will just tell you in which context the theorem of Falting's is proved. In fact, there are many proofs of this statement, all of which start in the following way. The main point is, now we're back to curves. Those are varieties, those are curves. Let's go back to curves. From experience, we know it's very hard to bound the number of points of a curve if the curve is in projective space. So looking at the curve in projective space is not a good idea to prove that theorem. Certainly not a good idea. So you don't want to try and find how many rational points a curve has by looking at the projective model, because it's well known to be very hard. But then what do we do, right? I mean, working abstractly is too complicated. And so the main point is the following. So let's say the context of proofs for the theorem part 2, for the Falting's theorem, essentially. And this is due not only to Falting's, there are many names that should be there. Voita, Mumford, Vail, Bombieri. I mean, this has been an amazing achievement, really amazing achievement with many. I'm sure I'm forgetting somebody, but certainly at least one has to mention Mumford, Vail, Neron, Voita, and Bombieri. At least these 5. I'm certainly forgetting some really big one, but is to place the curve not in projective space. We said this is no use, but inside an abelian variety. So what we do is we take our curve C, and to any curve C, you can associate a very nice abelian variety. An abelian variety is just a group. It's just an algebraic variety, which is also a group, an abelian group. The thing is that to any curve, you can associate a canonically given abstract and also projective abelian variety, which is just called the Jacobian. This is the Jacobian of C, the Jacobian of C. And I'm going to tell you what this is. It's very elementary. It has a very elementary description and a tremendous power. Because what you do is the following. You take the set, you begin by taking the free abelian group on points of C. Huge thing. A form of that. You quotient this out by a relation, which is called equivalence relation. And then you have this splits into pieces because this is an abelian group. So we have integer. These are linear combinations with integer coefficients of points. And so at each thing on the numerator has a degree. And this equivalence relation preserves the degree. So this splits into pieces, one for each integer. Take the part of degree 0 then of this. So this is the degree 0 part. So in the numerator, you have combinations of degree 0. And this is precisely the Jacobian. So this is the Jacobian of C. Okay, so, and it turns out to be an abelian variety. So it's a projective variety defined over whatever field C is defined. So if C is defined over Q, this is defined over Q, etc., etc. And because it's a group, it has lots of structure. It's a very nice group. Okay, one could have a colloquium talk just speaking about how wonderful the properties of the Jacobian is. For us, it's just enough to know that this, since you can embed, this is an embedding, so C sits inside its Jacobian as a subvariety in a non-canonical way, in many ways, but it doesn't matter. Because we can put C inside J of C, we can use the beautiful properties of J of C to arrive and prove this theorem after hundreds of pages of deep mathematics. But the message is, it's much better to put C inside its Jacobian than to put C in projective space. That's the message. Okay. Right. Now I'm just going to speak about something else related to this. Okay, now we have the rational points on curves behave this way. Now let's look at all curves together. Okay, so we are now going to geometry. Let's consider the set of all curves of fixed genus. Okay, this is denoted by MG. I'm sure that many of you know this. G is always the genus. I think it was written somewhere. It's here. It's the genus of a curve. So it's a non-negative integer. This is just a set of curves of genus G up to isomorphism. I should have written set here. Sorry, it's there. Okay. Curves of genus G up to isomorphism. Is a set. The reason why I wrote it is that for now it's a set. That's why it somehow slipped my mind. So this is the set of curves of genus G up to isomorphism. And the thing is that it's not just a set. Another big achievement of the past century is that this is a beautiful algebraic variety. Irreducible, connected, defined over any field. So over Q-press, okay? This requires some subtlety, but for now we are happy with that. So that's defined over any field of characteristic 0 of dimension. The maximum between 3G minus 3 and G. So this is just saying that if the genus is 0, then 0 is just 1 point, has dimension 0. If the genus is 1, has dimension 1. Otherwise, it has dimension 3G minus. We know lots of things about this, okay? And we call it a moduli space. So it's not such a great moduli space, but it is as fine as one can get. Okay, I'm going to have to skip a whole part. The question that so it is a moduli space. You have to think of this moduli space as putting together in one variety all curves of genus G. In particular, the curves of genus G defined over any field, and now I'm interested in number fields, so I will put a number field here. This set is the set of curves of genus G defined over K. Is in here, is a subset in there. So this is telling us that curves do not behave like crazy. They're just somehow organized in one nice, beautiful variety. And even if, as I said, the variety is not that nice, but it's so this is the part that I have to skip for lack of time, but let me just say there almost exists a family of curves over MG, universal family of curves over MG. So MG is not just the variety of G, but it has almost a family of curves of genus G, so that you find all curves of genus G over MG. But then you can look at rational points. You can say, well, but then maybe rational points also behave nicely. If the set of all curves of genus G behaves nicely, perhaps also the set of rational points behave nicely. I.e., they're bounded as a function, maybe of the genus, maybe of the field, who knows what. And this is, of course, what we want to conjecture. The conjecture that's been out for more than some 30 years. I mean, I'm going to write the strongest possible conjecture that is open. And then I will tell you that all its weakenings are also open. So here is the uniformity conjecture, and I'm going to call it strong uniformity. Again, this is not new. At least 25 years, maybe. It says the following: for every genus at least 2, there exists a number that depends only on the genus, such that in words, for any number field K, the set of curves defined over K having more than NG points is finite. That is, all but finitely many curves defined over K have at most NG points. So the following set of curves of genus G over K such that the set of rational points is greater than NG is a finite set. Now, so there are finitely many exceptions for every K. This number is universal, doesn't depend on anything, only on the genus. And you need to allow finitely many exceptions. So you couldn't have, this is very easy to show, that you must have finitely many exceptions. So this has to be there. It's not even, it's certainly false that the number of rational points of a curve of genus G is bounded by a constant that does not depend on the field. It's very easy. You can understand that by yourself. So this is as strong as you can get, and it's very much open. An easier version of this, so this is open. Maybe we're being too bold. An easier version of this asks for a bound that depends on the genus and the field, but that is also open. It is also open. It's not known whether there exists a number that depends on the genus and the field, such that every curve of genus G defined over that field has as at most that number of points. This is also open. This is what's called the weak uniformity conjecture. I didn't write. I won't. So let me tell you what's the strongest result we have. Has been proven. It's a really wonderful result proved recently. It's just the closest we get towards this conjecture. So this is a series of theorems. So I will write theorems, but in a unified statement by Dimitrov, Gao, Heidegger.
Excuse me, Lucia.
Yes, and Kühnen. Let me finish.
Yeah, sure.
Yes, question.
And the strong uniformity conjecture is so the number of points is at least that bounded from below.
No. So what this says is a fine. Okay, this is good.
Okay.
No,
yes.
But it's good that you interrupted me because so I went too fast. So first of all, I didn't say that, but there are infinitely many curves defined over any fixed number field. So lots of them. Okay, first. This may not be obvious, maybe it is, but first. So there are infinitely many curves for any K of fixed genus. this is saying that only finitely many of them have more than NG points. Okay. So it's okay. Yeah, I they may often write the points the wrong way, but this is not one of those cases. Okay. Other questions? So this theorem is as I said, I would put it in one word. This is last year. Part of it has been published, part of it is still in preprint form. It's very famous, probably you know this theorem, but let me just put it on the board. It tells you that for any G at least 2, there exists a number which I would denote BG, which depends on the genus, such that for any curve C over K of genus G, the number of rational points of this curve is bounded by a constant, which is BG raised to a certain power, and the power is 1 plus the rank of the rational points of this abelian variety. Let me write it first, R of C, and R of C is the rank of, as an abelian group, and so it's the rank of the set of rational points of this. This is an abelian group. A priori could have huge rank. It doesn't. This is, remember, this is a huge thing, but it's a very important theorem of Mordell and Weil that this number is finite. So this is by Mordell and Weil. This is finite. And this does depend on C and on K. But this is the strongest result that one has. I just wanted to state it because it relates to everything I said, and it gives you an idea. And I mean, this is a really amazing achievement. The proof, and this is the part I said I would skip to. So the moduli side of the talk has been somehow shortened. But what I wanted to say is that how do they prove this theorem? I won't tell you how they do it, but what's the context? Sorry, not the context. Yes, the context. The context. Yes.
So the statement is for every curve over K, the fixed K.
For every, yeah, because I didn't write for every K. For every K, sorry, yes. I'm sorry. For every K, there exists a BG such that, was that, yeah, such that, but BG depends only on G. So actually it didn't matter which way I wrote before because the dependence on the K is here.
Okay.
Okay, and for any C. Yeah, I didn't write for any K. So the context of this proof departs from this and places it in a universal context by looking at moduli spaces. So we had moduli spaces. I told you that there is almost a universal family of moduli spaces. And there is also a universal Jacobian. See, here this goes as follows. Take the curve, places it, put it into its Jacobian and work there. The part that I am, the point I want to make now in much fewer words than what I wanted to is the same can be done over moduli spaces because of the theory of moduli spaces of curves and of abelian varieties. So all the instruments that have been developed to prove the Faltings theorem can be established in the relative set of universal families. Okay? And let me devote, I still have 5 minutes. I want to tell you a little bit about this conjecture, why this is so important, at least in my opinion. And why, as I said, this is not new. This was there about 30 years ago. But this theorem and other recent discoveries in the area, many, I'm just giving you one, but there's been quite many results trying to bound the number of rational points of the curve. This is just perhaps the most important one, but there's more, right? All of this revived interest in this conjecture. There's a geometric reason why this conjecture is also quite interesting, and let me tell you why. So the theorem of Falkings so the uniformity conjecture, the strong uniformity conjecture can be viewed as a way of generalizing Falkings' theorem. Not only rational points are finite, but they're also uniformly bound. There's another way of trying to generalize Falkings' theorem, which is perhaps more direct, and that is what about higher dimensional varieties? How do you generalize Falkings' theorem to higher dimensional varieties? And this is what I want to say now. So suppose we have a variety V, smooth algebraic variety projected with as nice as you can take, of dimension anything. Now, what's the equivalent for a variety of, so a curve of genus 2, what's the right generalization? C has genus at least 2 as a generalization, which I will not define. I will just put the word on the word. If C is of general type. I will not tell you, and this definition works for varieties of any dimension. I will not tell you what a variety of general type is. I will not tell you precisely what a variety of general type is, but geometrically I will tell you that it has to do with the dual of the tangent bundle. This is a smooth variety, it has a tangent bundle. To be of general type is to say that the tangent bundle of V, dualized, so this is what we call the cotangent bundle, is positive, whatever positive means. Okay? Has to do with the positivity of the cotangent bundle. And the reason why I'm writing this is that I want to convince you that this is geometry, okay, and not arithmetic. So a curve is of general type if and only if its genus is at least 2. By the way, you may it's actually I'm just contradicting what I just said. Let me spend one more word on varieties of general type. Let me tell you which varieties are not of general type. Projective space is not of general type, for example. And projective space has, if you take a field large enough, a number field large enough, no, projective space always. A projective space has always lots and lots of rational points. Rational points are dense in projective space. Abelian varieties also are not of general type. Okay, so these are varieties that are not of general type. So there's a famous conjecture of Lang, which is called the strong Lang conjecture, that aims at generalizing Falkings' theorem to a variety of higher dimension. It says the following. For every variety V of general type, there exists a subset closed in V such that all but finitely many k rational points of V are contained in C. So I forgot to say that V is of general type and is defined over K. And K is any number field, for example, Q. This conjecture says that the rational point, this closed subset is such that the set of rational points of K for any, let me be more precise. Say V, let's make it simple. Suppose our general type variety is defined over the rational, okay, so over Q. Okay, this is easier. Then there exists a closed subset Z of V such that for any number field K, so the set Z does not depend on a number field now. the set of rational points of V are all contained in Z up to finitely many. So we would like to say that the set of rational points of V are contained in Z. This is clearly false, but it becomes true if you exclude a finite set, which we call E sub K. This depends on K. So the set of rational points minus finitely many of them are contained in C up to finitely many points. This is the strong line conjecture. Way open. And just like the uniformity conjecture in its strong sense and all of its weakenings are open, also all the various weakenings, natural weakenings of this that you can think of are all open. Okay, so I gave you the strong line conjecture because I wanted to tell you how bold we can be without being able to disprove it. We cannot disprove neither this nor that. And again, so what's the relation between the two? And this is where I wanted to get to tell you at least something I did, even though not alone. So there's a theorem proved in two states, 97 plus 21. Yeah. The theorem says that the strong line conjecture implies the strong uniformity conjecture. So there is a this is a theorem which is based on geometry. So that theorem is all about the link between geometry and arithmetic. Of course, it's a conditional result, but it gives you, that was the main theme of this colloquium, tell you about the relation between the two fields, okay? So one word about this theorem. In 97, we proved the weaker version of this, but we didn't realize that. So we actually claimed that the strong version was true, and it was not true. We had to work again, and it took us quite some time to. So what we proved, and I'm out of time, let me not bore you with this, but we had a weaker version of this, which took, you see, many years to be fixed. And thank you for your attention.
Thank you very much, Lucia, grazie molte per questa bellissima conferenza di introduzione fino alle ultime pagine. E allora passerei, se ci sono domande, anche qua. No, su.
Singolari, ci sono dei risultati diversi, per una curva singolare.
Allora, la domanda è per chi è lontano e se ci sono risultati per curve singolari. Sorry. The question is if there are results for curves that are singular. The answer is all results for singular curves boil down to the same one for smooth curves. So as far as I know, the answer is no, nothing special, unless you have something specifical in mind. So you were talking about rational points and everything for, so the answer is not that I know, nothing special.
Other questions? So just a curiosity. The converse implication is.
I think no one ever tried that. Actually, not that you asked that. No, I think no one has ever thought of that. You're right. I don't know. It's quite fair. I don't know. The proof is very geometric. It's all about modular spaces, actually, again. But no, I think it's way out of reach. I don't think, I wouldn't even know how to try it.
You would say is false, or I mean that one is stronger than
I don't think, on a first guess, I would say no, I don't think it's true. But still, those are conditional, those are conjectures, so it could be true, but I would guess I wouldn't have any.
Thank you. So other questions?
It's that general type means G greater than or equal to 2. But on the other side, you have the exogenous element, no? Because the number mg depends on the genus.
Yes.
So I don't see where, so it's complicated on the risk because the definition there of conjecture, there is no G.
Right, that's because I didn't, yeah, I mean, the thing, I didn't explain why. I didn't even say a word. So the fact that the curve has genus at least 2 has to do with the number of holes of the corresponding. But it's also, and this is a baby Hodge theory, it also depends on the sections of the cotangent bundle. Roughly speaking, is that G is the dimension of the space of sections of holomorphic differentials. And holomorphic differentials means the cotangent bundle of the curve. And so if G is at least 2, it means that there are some sections. So it's not 0 or 1. It's not either empty, the space of sections of the cotangent bundle or curve, and it's not a constant. It actually has some sections, hence it is positive. Okay, so the thing is that G is the dimension of the space of sections, and I'm going to have to write some horrible thing here, of the cotangent bundle of C. This is a vector space. If this is at least 2, it's a non-trivial vector space. If the G is 0 or 1, it's a very boring vector space, right? Okay, so if genus is at least 2, we say that this is positive. That's the connection. But there's nothing like the genus for high-dimensional varieties.
Oh, yes, thank you. But so the question is a little bit different. So I don't see that, in a sense, how to control the G that is there on the left from the G that there is no exact G. Just see G is less bigger than 2. I don't see the. So here you have on the left an estimate with the depends on G. And I don't see.
I don't.
No, maybe I don't.
There's no G here.
Exactly.
This is exactly why it's quite no. But this is really amazing. That this conjecture, this conjecture is very strong. So one exercise is to see that if B is a curve, then this is saying that B has finitely many rational points, and they are bounded. This is an exercise. Not that easy because I gave you the strong version, but there shouldn't be any G here. There is no G. Or perhaps, oh no, okay, wait. But there's another thing. One thing is true. Let me just say one thing that is true, not conjectural, is that if this G exists, the limit, this is something we can prove. If it exists, the limit for G that goes to infinity of Mg is infinity. Okay? So that you have to have G here. There's no way you can get rid of G. This is something one can prove. Okay? So maybe that settles. So you have to consider all curves of genus G together.
You have something uniform.
Yeah, but the set, but the set Z depends on V. The set Z depends on V.
So here we have a question from Armando Capasso who asks about strong line conjectures. Could the EK empty?
No. The answer is no. It's easy to find examples. The thing is that the question is, so could EK be empty? No, the answer is no, because this Z does not depend on a number field. So suppose EK is empty for some K. Take a point outside EK take the first, the smallest, okay, let's just be quick. Take a point outside take a point outside of Z, take the field extension of K such that that point becomes a rational point, and there you have already a point in K. So I'm saying that you can, if you take an algebra, any algebraic point on a variety, but not in K, in an algebraic closure, you take a point in the algebraic closure, you take the field that contains that point, the number field that over which that point becomes rational. And if you took that point not in Z, there you have it. So no, EK for K large enough has to be there.
The questions?
Yes. You see that in the case of projective spaces, the rational points are dense, and in the case of the variety of general type, we have the conjecture. And what about the intermediate case? For example, if the codal dimension is greater than 0 but less than
Lots and lots of conjectures. Basically, very little is known. So for rational varieties, for unirational varieties, for rationally connected varieties, this is easy. Rational points are dense. For abelian varieties, there exists a field over which they're dense. But then it gets very complicated already for surfaces. Already for surfaces, there is no clear picture. But so thank you for your question, because that gives me the possibility of saying that, you see, this conjecture is certainly false for a projective space, because projective space at the set of rational points is dense, and also for abelian varieties. So I gave you the two examples of varieties that are not of general type, but then I didn't comment, but now I'm doing it, on the fact that the conjecture will certainly be false for those. Thank you for the question.
Other questions? So we thank Lucia again. Claudio.
Well, I'm here. I'm here again. Maybe I'm not. Yes. I like to thank Lucia for a beautiful talk. One consideration: this time we tried to have a mixed type of colloquium, and the experience that we had shows that being together in a room, it's much easier and much more effective than being sparse away, dense all over the country. On the other hand, this opportunity of recording and broadcasting the colloquium enlarges a lot the possible audience, and for sort of a celebration like this event is it's nice, and thanks to the beautiful talk, we had really a wonderful time this afternoon. Thank you again to everybody, to those who contributed to organize this colloquium, and thank you again, and I'm sure that we will meet again soon in person, and maybe we also with this mean of communication that is YouTube or Zoom for those who were on the Zoom room. So thank you again, and for tonight is over. Thank you again to everybody.